All right, welcome back. If you've been following along with this whole series, you've been in the trenches, piece by piece, building a robot's mind from scratch. Well, today is the capstone. This is where every single thing we've learned gets a massive revolutionary upgrade. We're making the leap from pure code to actual cognition.
So just think about that for a second. All that hard work on kinematics, on planners, on state machines, it's incredibly powerful, right? But what if you could just skip all that? What if instead of programming every little step, you could just show the robot what to do and it would just learn? That's the huge question we're diving into today.
But first, let's take a moment to appreciate what you've already accomplished. Through those first 8 labs, you have built what we're going to call the analytical brain. And it's truly a masterpiece of engineering, a really complex, hand-coded system where every single movement is planned and precisely calculated. And you can see how all the pieces fit together. Your kinematics work laid the groundwork. Impedance control gave the robot that gentle, compliant touch. The planners made it smart enough to not bump into things, and the state machine taught it the sequence for actually grasping an object. It all came together in that amazing whole-body controller from Lab 8. It's the peak of this analytical approach, a powerful but pretty rigid pipeline. Okay, but now we are about to make a huge leap. We're introducing a totally new way of thinking, the learned brain. And the core idea here is absolutely wild. We're going to replace that entire intricate hand-coded pipeline you built with a single, intelligent system that just learns by watching. The magic that makes this possible is a concept called vision language action, or VLA for short. You can think of it as a totally end-to-end system. It takes what the robot sees with its cameras, listens to a command you give it in plain English, and then it directly outputs the physical actions. It just skips all those intermediate steps we had to code by hand before. So this is the big idea, right here, this transition. We are fundamentally changing how the robot thinks. We're going from a system that meticulously follows a pre-programmed script to one that can generalize and figure things out based on a high-level goal. It's really nothing short of an evolutionary leap in robot control.
Okay, so you're probably wondering, how on earth does this learned brain actually work? Well, let's pop the hood and take a look. We're going to trace the flow of information from a simple sentence all the way to a complex robot action. At a high level, it's a pretty straightforward 4-step process. First, the robot has to sense the world around it with its cameras and listen to our language command. Second, it has to encode all that raw data into a mathematical format it can actually work with. Third, the real brain of the operation has to decide what to do. And finally, of course, it has to act, sending out the commands to move its joints. So let's start with that first step, sense. The robot actually has 2 eyes, and this is a really clever bit of design. There's a camera on the wrist that gives it this close-up first-person view, which is perfect for precise manipulation. And then you've got the head camera, which gives it the big picture, the overall context of the scene. The combination is so good it can get depth information without even needing a special depth sensor. Now for step 2, encode. Those 2 camera feeds get crunched by a couple of neural networks called ResNets. The text command, something simple like pick up the red cup, gets converted into a string of numbers by a language model called CLIP. And the really cool part here is that the CLIP model is frozen. It's pre-trained. It already understands English, so we don't have to teach it. Finally, the robot adds in its own sense of body awareness, proprioception, which basically tells the brain where all of its own joints are at any given moment. And all of that data, the vision, the language, the self-awareness, it all gets fed into the heart of the system, the ACT policy. This thing is the brain. It's a transformer model, which you might have heard of. It's the same kind of tech behind things like ChatGPT. It takes everything in and acts as the central decision maker, figuring out what to do next. So we have this really powerful brain. But how does it get so smart? It can't just figure out how to pick up a cup on its own out of thin air. No, it needs a teacher. It has to learn by watching an expert do the task perfectly, thousands and thousands of times. And this is where the whole thing comes together so beautifully. Who's the expert? Who's the teacher? It's the very system you already built. That hand-coded analytical brain from Lab 8 is used to generate thousands of perfect demonstrations. The old system literally teaches the new, smarter, more flexible system. It's just so elegant. This whole process has a name. It's called behavioral cloning.
All the learned brain does is watch these perfect demonstrations. It sees the camera images, it gets the command, and it sees the expert's actions. And its one and only job is to learn to produce the exact same actions for the exact same inputs. It's basically just a super advanced game of copycat. But, just copying isn't quite enough. If it only ever sees one perfect example, it'll just memorize it. To make the policy truly robust, we use a trick called domain randomization. As the expert is collecting all that data, we're constantly changing little things. We'll shift the object's position a bit, change its color, mess with the lighting. This forces the policy to learn what actually matters, like the general shape of a cup, and to ignore all the details that don't, like the exact lighting in the room. Okay, so we have a teacher, we've gathered tons of data, and we've trained the brain. So what's the payoff for all this work? Well, the payoff is what we've been aiming for all along: smooth, intelligent, and completely autonomous robot behavior.
I want to start with just one number, 10. What could this possibly mean? It's not random, I promise. This number is actually the secret to making the robot's motion look graceful and natural, instead of, robotic and jerky.
It's a technique called action chunking. See, instead of deciding what to do for just the very next microsecond, the ACT policy actually predicts a whole chunk of the next 10 actions all at once. By planning just that little bit into the future, it can create movements that are way more coherent, way smoother, and more purposeful. And to put the final layer of polish on top, there's one more trick called temporal assembling. The best way to think about it is like you're drawing a smooth curve. You wouldn't draw it dot by dot, you'd connect a bunch of short overlapping lines. That's what this does. It smoothly blends the end of one 10-step chunk with the beginning of the next one, making sure there are no sudden, jerky transitions. The result is just incredibly fluid control.
And finally, there's one last little practical trick for deployment. The model is trained using really high precision numbers. But to get it to run fast enough on the robot's actual computer, it gets converted to a simpler number format in a process called quantization. The bottom line is, this is what gives us the real-time performance we need, letting the policy make decisions more than 10 times every second.
And there you have it. That's the end result. All this theory, all these components, it all boils down to this beautifully simple outcome. You give the robot a command in plain English, and it just autonomously figures out how to get the job done in the real world.
And that really brings us to a final mind-bending thought. We've just seen a system where a robot can learn a complex task just by watching an expert. Now that this is possible, what's next? If a robot can learn just by watching us, what is the limit to what it can learn to do?